have previous class we have derived, so good afternoon everybody. So, today we are going to discuss we are going to continue the lecture on the on the cell buckling, and if you can briefly recapitulate what we have done until previous class. So, we have derived the Donnell equation and we have stated the assumption clearly. So, if you can briefly recapitulate or briefly recall little bit what we are discussing. So, from the in the beginning we have presented a equation simplified formulation for the buckling of cell, in which we assume the axisymmetric deformation, right, and then we have derived by using a small strip of the cylindrical cell, and we have seen that we have obtained some equation which is similar to the buckling of beams in supported on elastic foundation. But then we have seen that this kind of solution what we obtained is hardly followed, except in the initial regime of a short and thick cell. Okay. So, then we started to and then we have solved the equation. Nevertheless, it gives us the correct dependency, that the buckling load under axial compression, uniform axial compression uniformly distributed along the circumference, okay, that the dependency of E h square by r, that is clearly represented by that. Okay. But then we started putting more and more physics into it, and then we derived the Donnell equation for which governs the buckling of cell, and Donnell equation for cylindrical cell, right. So, and then there was a certain assumption. So, we have presented a simpler derivation following Bajan, and the prime assumption there was several assumptions made. First one is that the cell we assume to be shallow cell or quasi shallow cell, okay, which is given by the fact that in whatever the buckling modes, the wavelength of buckling mode are much smaller comparing the overall length of the of the cylinder, and then pure bending is valid, that means plane section remain plane after deformation, there is no shear deformation, right, no. And along with that, another important thing, very important thing, is that there is no initial curvature. So, there is no initial imperfections in the cylinder, okay. And if you can recall, the governing equation looks like d lambda square, and d is nothing but flexure rigidity of the cell section. So, it is nothing but E h cube divided by 12 into 1 minus nu square, same whatever was in plate. So, the derivation follows very similar to the cell, except that the additional strain term is coming out of curvature, okay, curvature geometry, okay, and there was some additional term was also coming, but those terms, some of these terms were neglected given the fact that r is very large comparing the other terms. So, whenever there was 1 by r, denominator 1 r term was there in the denominator or r square, we neglected those terms in the strain expression, right. So, this was the equation, if you can recall. In the book you will see lambda to the power 8, but essentially I am writing in this form. So, xy minus this is lambda to the power 4 in xx 0 w comma xx plus 2 on xy 0 w comma xy plus n yy 0 w comma I plus E h by r square w comma xx is equal to 0. So, and you see that lambda is nothing but Laplacian operator, which is del square del x square plus del 2 del y2, right. So, here see, Donnell equations can be linear or can be non-linear, because if we consider this to be fixed, constant, then of course it can be it is linearized, right. But because of this initial curvature and initial deformation, it is not so that there will be no nxx 0. So, there will be all these terms present, and then with the incipient deformation, this terms is going to modify. So, that way if you consider it, can be non-linear, okay. So, please but Donnell equation is mostly used to find out the critical load. Okay. So we will present several solutions. The first one is a cylindrical cell, under axial compression. Axial compression. So here we see length is L, radius is R, and then it is subjected to nxx0 because longitudinal axis is x. Okay. And if you see other two, so y is along this and z is perpendicular to this. Okay. So this is one cross section of the cylinder, so this is circular. Okay. And this is of thickness h, right, h thickness. So that is the choice of coordinate system, right. So of course from here initial stresses, so what we see here, nyy 0 is 0, nxy 0 is 0, and then we are having only, and there is no external load, P is equal to 0, no lateral pressure, P, no lateral pressure. So only thing that is remaining in nxx 0, right. So with this, when it is, now it is going to buckle. Now we know that initially, when we consider axisymmetric deformation, we have seen that we will have this, buckling pattern will look like something like this. You see that? This kind of, wavelength will be there. So these are all half wavelengths. So it can be expressed, the solution along x direction can be expressed as a sinusoidal function, right? Maybe. And similarly, earlier when we were considering axisymmetric buckling, what we assume that here the circular section which is having initial curvature r, that was extending with the amount w, right. So now the radius is increases from r to r plus w, but we didn't consider any circumferential over that. Okay, we didn't consider any sinusoidal kind of, so we didn't consider any circumferential wave number wave. Okay, right. We have considered that because of the axisymmetric assumption, it is just expanding, and then that allowed us to take a small section and to write down that governing equation, fourth order. Okay, then we have considered the equilibrium of a small element, and that's what we have solved, right, for the axisymmetric. But here that is not the case. Here we will also assume that along the circumference, along this, so just like in longitudinal direction, along circumferential direction also there can be, if you consider, there can be this kind of, this kind of, so we will approximate the lateral circumferential displacement field using sinusoidal function. So these are the half wavelength number. Okay, we are going to assume that here this wavelength is L and this wavelength along the circumference is B, right. So as you see, for shallow cell approximation, we are considering this total length is small l, right. So please note that for the shallow cell assumption, B must be very, very lesser than R, right, and L, right, or rather R, L, and capital L is also very, very small than L, right. These two are there, right. So we will assume that the solution can be taken as cosine of, and you see it must be odd function. So alpha x, cosine of beta y. Alpha and beta are the half wavelength number, alpha and beta. So alpha is basically pi upon L and beta is equal to basically pi B. These are the half wavelength number, okay, alpha and beta. So L and B are the half wavelength, half wavelength of the buckle of the longitudinal and circumferential buckle, circumferential buckle. So with this, then what we will do? So with this assumption, we can substitute in the governing equation. So the way you see that, so lambda operator is del square del x square, right? Del 2, del y2. So if you see it differentiate twice, so it will be what? Minus alpha square and minus beta square, right? Twice, right? So then if you consider the governing equation lambda square, 8 to the power 8. So this is going to, so then if you substituting this solution, substituting in the equation, in the Donnell equation, Donnell's equation. So what we are going to get? Please note that when we are assuming this, or not considering that much about the boundary condition, but please note that if you want to satisfy the boundary condition, you can also assume sin, that's not a problem. Okay, here we are assuming cos, but you please see whether it satisfies the, here we are assuming, we are yet to enforce the boundary condition, but please note that if you want to enforce boundary condition, that see, it is simply supported, then it is better to assume sin, right? Okay. So then with this, if you substitute, then it will look like differential equation will be substituted to algebraic equation to the power 4 plus EH r square alpha to the power 4 minus sigma xx into h. Sigma xx into h is nothing but nxx 0. Why I am putting 0? Because it is constant, okay. Alpha square and alpha square plus beta square is equal to 0. So you see that this is a homogeneous equation, it is 0. So that's what is a eigenvalue problem, okay. And these are nothing but the eigenfunctions. If you consider this is W0, you see that W0. So W0 this, so it can take any value W0. So these are the deformation patterns. So these are the eigen modes, and W0 doesn't really matter, right? From here, you will see if you simplify, then you will get n xx 0 or is equal to n xx critical load is basically E h divided by pi square r square L square 1 by L square plus 1 by b square to the power minus 2 plus pi square L square d 1 by L square plus 1 by b square, okay. Please note that these are all shallow shell theory, so L and B is very, very less than R, okay, very, very less than R, okay. This, sorry, it's not very, very less than L with respect to R, okay. R half wavelength are much, much smaller than R. That's what the shallow shell assumption based on which the Donnell's theory is, is derived, right. So what we see that this solution, of course, how many L and B will be there? We have to minimize this thing, right. So we have to minimize it with respect to L and B, the way we have done in plates and others. So for certain combination and L and B, which are nothing but the half wavelength, half of the wavelength, that with respect to that we have to minimize this. So we have to, this result into a minimization problem. So now, so this minimization people have done, they made various assumptions. For example, the people who have, scientists who have contributed profoundly here is Chazes, whose book we read, Alexander Chazes, and then Caladine and others, okay. So minimization we are not going to present here, but we understand that here this need to be minimized, differentiate with respect to L and B, and then So, it is a basically two input variables are there. You have to minimize with respect to L as well as B. So, you del pi del L del pi del B is equal to 0, and then you have find it. So, if this is unconstant minimization, so you will see, but we will consider some special cases. Okay. So, if you see the special case, for one case, we want to see whether it mimics the one which you have with the one where we started the discussion for a axisymmetric cell buckling. Okay. So, for the axisymmetric case, B tending to infinity, and that means it implies beta tending to 0. So, beta tending to 0, then cos beta y tending to 1, right. So, when B tending to infinity, that means what? The half wavelength is very, very large. That means along the circumferential, and B is nothing but the wave number along the circumferential direction, right. So, what it means that there is only one, so one of the wavelength, half wavelength is so large means there will be only one wave number here, you understand. That represents nothing but the axisymmetric mode, right. So, this one is the one which is axisymmetric mode, and this was the axisymmetric mode that we have, for which you have derived earlier. We let us see that whether it is mimicking that. Okay. So, then for this case you will see that W x comma y is nothing but W0 cosine of alpha x, and W0 cosine of alpha x. This is cosine of alpha x, means now you have only longitudinal wave numbers, right, wavelengths, and then so this basically these mode shapes correspond to axisymmetric mode that we have discussed. So, what we see that Donnell's equation mimics as a special case the case of axisymmetric buckling, okay, where the circumferential dependence you are not taking into account, assuming the axisymmetry of deformation, and then only one single mode is governing, okay, zeroth mode you can consider, and that is what this term dropped, and essentially that was a differential equation in terms of x was only the independent variable, right, isn't it. So, that okay. So, with this then, so we can mimic that case. Now, we will now distinguish between two different using some variable z, okay. Now, for axisymmetric mode that is given. Now, for doubly periodic mode. So, for W periodic mode means what? Where both the longitudinal and longitudinal wave numbers will anyway be there, right, but W periodic in the circumferential direction. That means it will have a combination. This means a combination of L as well as B, both. So, wave numbers are there both. So, here along this direction wave numbers are there but here circumferential also it is there. So, it is something like that, okay, or some So, for doubly periodic mode, and if you by satisfying the boundary condition, so for different cases you have to satisfy the boundary condition. So, that means when you assume this cosine sine function, that is where when you satisfy the boundary condition, those things you have to keep in mind, right, which functions you will assume, okay. So, for that, for example, simply supported boundary condition, simply supported boundary conditions, right, simply supported boundary condition. For that, minimum, where you will look at the minimum critical load for simply supported boundary condition. So, minimal critical load will be given, minimum critical loading will be given by the cell geometry. in which the length and 2 pi r, that is the radius, length and radius can accommodate an integer number of half wavelength, right? So that is very important. You have seen that, right, in plate, that wherever our plate dimension B is such that plate length that it accommodates the integer number of half wavelength, that's where it was minimum, right? Can we recall that, you know, the Arnold term structure, right? It was something like this, something like this, something like this. So what is happening? If it is integer, you know, if it is integer, then it is attaining minimum value, right? Otherwise, in both the direction, it is going up, because that is giving an energetically favorable configuration, right? So same thing here as well, okay? So boundary conditions also have influence on the critical load, right? So then we will distinguish between the two cases. One case is for long tube and high number of buckle, and long tube means long cylindrical cell, and high number of buckles, number of buckles along the circumference, So for that, people have done unconstant minimization, okay, unconstant minimization to obtain the critical load, okay. And to obtain the critical load is NXS critical is 1 the root 3 mu square EH square by R. You see that dependency H square by R, and here please note that there is a parameter. This is valid for Z greater than is equal to 2.85. Z parameter is called Bartt-Dorf parameter. That basically distinguishes between the short and long cell, okay. Later other parameters were also introduced, like omega and other parameter by the European code, but I am not discussing that. But this, so it was done is in the Bartt-Dorf in 1947, the year we and India attained independence. For Z greater than 2.5, that case basically represent where this cylinder is long enough and there is many buckles actually along the circumference direction. Then if you do constant minimization, that means minimizing with respect to L and B, then you will see this kind of critical load. So that you get a closed form expression by doing the minimization with respect to L and B, minimization with respect to L and B, half wavelength, 1 by root 3 1 minus nu square EH square by R. Do you see the dependency on EH square R is universal, okay, but this is for the, so since Z greater than 2.85, this is the long cell, right. Similarly for short cell, for the case, you know, for short cylinder, where Z is greater than 2.85, okay, NXX here 1 plus 12 Z square by I to the power 4 pi square d L square. This formulation was given by Chazes, okay. So this is for short cylinder, okay. Please note that the parameter that is distinguishing between the two is long tube with high number of buckles along circumference, and the short cylinder is of course the Bartt-Dorf parameter, and there is a critical value for that 2.85, okay. However, there is a note, there is a point here. Please note that here. The note is that, here only half, only one half wavelength, only one half wavelength, span the entire circumference here, the entire circumference here. That means d is equal to 2 pi r. See, for this, whatever has been obtained by Chazes in around 1967, you see that unlike this one, here a large number of buckles happens along the circumference, right? But here for this case, only one half wavelength span the entire circumference. What does it mean? That means one means it is very similar to the axisymmetric this one, right? B is equal to 2 pi r, right? Half wavelength is nothing but this. This is contradictory to the shallow cell assumption, right? Contradicting to shallow cell assumption, right? Shallow cell assumption. Why it is contradicting shallow cell? Because in shallow cell assumptions, what we have assumed that B is very, very smaller than r. So, this cannot be correct. So, this expression is not very correct. It is not very accurate, not very accurate, And you understand why it is so. Because although we have solved the mathematics and you have obtained that, but the thing is that since V is 2 pi r, it is not very, very less, only one wave number is spanning over the held circumference. So, this is contradicting the fact based on which the Donald's equation has been derived, which assumes that the shallow is shallow cell assumption, right? That be okay. Now, in case two other extreme cases we must consider here. If the cell is very, very long, when cell is very high, then what happens? Then buckling cannot be governed by the Donald equation. Why? It will behave like a long, so for very long cell, it's right, it's like behave like column, like long column, not governed by, it is not by Donald equation, This is not governed by Donald's equation. Please note that, okay. Another thing, if cell is very, is very short means, Z tending to 0. So, please note that, whether when we are discussing that Z greater than 2.5, less than 2.85, it is not encompassing the very long and very short cell Z tending to 0, then the cell will behave like a, it will behave like a plate, because very short cell, that means it is so individual, this one, it is so, short, then, so short, so that means, the cell action will not be there. So, the things will, it will behave like a plate, you see that, and then its buckling will be governed by the blade wheel, right. So, other than these two cases, there are two extreme cases also, in which one case is for very long cell, which behave like a long column, okay, and for very short cell, Z tending to 0, Z, so it behave like plate, right, good. Another, so with all these things, there is other very, very important thing, which is even most striking fact, most important striking fact of this solution, So, you will see that in case there are multiple solution involving doubly periodic mode, what is doubly periodic mode? Doubly periodic mode means along x direction, along the longitudinal direction there are modes, and then along the circumferential also modes will be there. Okay. So, doubly periodic mode and axially symmetric mode, if we consider, and the first one is the axially symmetric mode, right? Axially symmetric mode. You know which one is axially symmetric mode, because the one half wavelength span over the entire circumference. So, you see these are the two modes. Initial mode, if you consider fundamental mode and things. So, what we consider axially symmetric mode in the case where there is only single wave number span over, and then doubly periodic modes means there is several two wave numbers along the whole circumference. Now, here also in doubly periodic mode there can be combinations of B and L, right? Combinations among B and L. Why combinations among B by L? That means along the circumference, along the you can have you like having like this, right? So, you can have like this, right? And then you can have, so what happen is that, of course, here I am having more modes, okay, more wave number, but you can consider then two wave number. So, there can be combination between the longitudinal as well as circumferential half wavelength, right? So, when I am calling doubly periodic mode, if we have doubly periodic means, say, consider that this is one, this is one, this. So, this is one complete period, right, and this is one complete period, right, along the longitudinal. And now, in the circumferential, this is on one complete period and this is one complete period, right, right. So, the here wave number is basically half wave number is 1, 2, 3, 4, here is 1, 2, 3, 4, right. So, there can be n number of combination between the two, these two, right, this and this can be outward, inward, like something like that, right. There can be various combinations of that, there can be 4 into 4 type of combinations, right. Now, it has been seen that if you consider even axially symmetric mode, or you consider doubly periodic mode with any combinations among B and L, then a very interesting striking fact is that the critical load among this mode, among these modes, do not vary considerably, do not vary considerably. That means less than 2%, less than 2% variation, 2-3%. Okay. So, what I am trying to say is that the critical load among these modes, whatever solution you obtain by solving Darnell's equation doesn't vary. What does it mean? That means cylindrical cells, cell under axial compression have closely spaced mode, right? Closely spaced or multiplicity of mode, and when it is having multiplicity of mode, that means they will interact, there will be modal and all these modes. See, In linearized regime, there will be no coupling, but please note that they are coupled anyway by geometric nonlinearity, right. I emphasize that we can linearize it, but Donal equation is nonlinear as well, because nxx0, nyy0, nxy0 are always with incipient deformation, they will be changing and there will be coupling. So, there will be these, all these modes are geometrically coupled, all these modes, okay, all these modes are coupled coupled mode. So, they interact, right, coupled, and this lead to modal interaction. You see this modal interactions, and when this modal interaction is there, that basically reduces the load, reduces the critical load. From the very beginning of the classes, I have shown that when there is two modes interacting, then the combined mode will have a much reduced load, because it become imperfection sensitive, right. Two coupled mode with the same or closely spaced, closely similar or very close critical load, they interact if they are coupled, right, and they will further reduces the load. We have demonstrated this phenomena using Auguste's column, right. So, this will significantly reduce the critical load, and that is why you will see there is significant difference. This shows shows significant difference, significant disparity between theoretical and experimental and experimental critical load. You see that? So, the way it will show, it is Z, and here I will just show you that. So, this is the most interesting or fact out of all these things, because the solution of the Donal's equation give closely spaced mode, okay, and then if you plot it for the varying of Z, and then if you normalize it the nxx critical, you normalize it with pi square dz by L square. Here is logarithmic, and this here also it's So, you see from here there will be huge drop, you see that. So, whatever this critical load is, some kind of upper bound it is forming, but there is a significant drop in this load. Why this drop is happening? Because all these closely exposed mode conspire through modal interactions, and they reduces the load. That of course, in order to study that load drop, you have to you have to solve it by accounting the non-linearity, and that is we are going to we use a little different version, but essentially the elements are same to show this drop. Okay. So, this is the most interesting fact here. Okay. Now, please note that for the cell under axial force, this kind of drop in critical load is occurring, but this is not so. Please do not, you should not be misguided with the fact that for all the cases this will be true. No, this is not the true. If the cylinder is subjected to transverse load along with axial force, lateral pressure, be it hydrostatic pressure, or instead of hydrostatic pressure, if you you can simulate this situation condition by two ways. One, you take a cylinder and then you compress it. At the same time, you can hydrostatically apply pressure. That way, you do this triaxial test in in solid mechanics. Either you can apply you can pump up liquid to pressurize, or another easier way is use suction pump to take air out. So, atmospheric pressure will push it. Okay. So, if you do this, then you will see a little different kind of thing. So, what we will see, that I will do now. So, what we have understood from here, that we distinguishes between long and short cell. Of course, there can be super long, there can be super short, okay, and then the Bartdorf parameter is the one which distinguishes between the two. Of course, for very short cell, the things Z less than 2.85, it is not very quite valid, because that violates the cell assumptions into summarize. And then most importantly, it gives you the huge reductions in the critical load, because of the multiplicity of multiplicity or closely spaced mode which are coupled otherwise geometric nonlinearity through geometric nonlinearity, and then there is an interaction between the modes and that reduces. So, that modal interactions is a very important thing here, right. So, but please note that all this reduction in load, so there is a huge discrepancy between the theoretical and then practically observed load. That will the theoretically we will see that how it can the drop can be obtained, but okay, this at least this analysis will not be able to predict that, but it can definitely predict the closeness of the mode critical load between different modes. So, now we will consider a case, the cylinder subjected to both axial compression and lateral pressure. So, a cylinder which is both axial compression as well as lateral pressure, if you consider this one, right. Okay. So, here it is axially compressed, is nxx0, and this pressure this is P. So, for this case, once again you can, for this case, initial membrane stress, you see nx, initial nxx will be of course nyy by 2. You just apply the hoop stress and meridional stress, that theory from the undergraduate mechanics. Nyy is minus p capital R and xy is equal to 0, right. Membrane, this is the membrane state subjected to P load, right. So, we basically we are converting how P can be given as input in the Donnell equation, because Donnell equation can only takes care of the membrane stresses. So, we can take care of that, right, by substituting. Of course, nxx already have nxx 0 over there. So, and if you do take this and then substitute in the governing equation, so assume W is equal to, once again the similar solution, sine of alpha x cosine beta y, right, and alpha beta, as you know, half wavelength, right, y by L and beta is y by b, right. Then I am not doing it, but you can easily do it, it is not a problem. Donnell's equation, you can the assumed solution and then assume this nxx of value, we can substitute. Of course, here will be two unknown on although one equation, so we cannot solve for it, we can only solve for by assuming certain ratio between nxx0 and p, because there are two unknowns. So, we will define some ratio rho as ratio as nxx by nyy. This ratio we are going to define for the critical one, right, and then you will see the way we will obtain that P critical is 1 by K Now here rho is this ratio of the nxx by nyy, and this this parameter k is alpha into r, and then n is nothing but beta into r. R is the radius of the cylinder, right? So you, as you see that P critical you are obtaining, but as a function of this ratio, okay. Ratio is nxx and nyy, right? It is rho, right? Because you have only one equation. But what I would like to tell you, so that now this you are obtained from Donel equation, right? This is Donel's solution, right? Donel equation. Huh? So this Donel's equation we will see. So m and all other parameters we have defined. We have defined k, we define n, and m and n. Okay. So here, then I will what happened here. There is an interesting fact. Here I am going to plot log z, and here I am going to put PCR divided by y square dz divided by L square R. Rho is equal to 1 by 2. Okay. Here you see that. So this solution is given by Donel's, right? And this all this data point is coming from a experiment. These are from experiment, and these experiments were conducted by Goddard. Okay. Goddard has many experimental contribution on inelastic and this buckling of cell, and this is also he has also proposed these solutions. So that's what Goddard has proposed. So you see that they are a reasonable match. So what is really happening over here? The thing what is happening here, if you see the P critical for different combination of k and n, you see, okay, or alpha beta rather, then you will see they are not well spaced. Okay, here the modes are well separated. The modes are well separated. That means modes and there is no multiplicity, no modal multiplicity. Okay, multiplicity. So they do not interact. Since there is no interactions among these modes which are coupled, there is no decrease in there is post critical load drop is not there. So there is a good match between experiment and theory. So what we see? This is an interesting fact that cylindrical cell, if it is only axially loaded under axial compression, then it shows imperfection sensitivity because of this closely spaced mode which interact, right? And there is a huge difference between experimentally observed load and then theoretically predicted load. Whereas, if the same cell along with axial compression, if it is accompanied by lateral pressure, okay, then the imperfection sensitivity is essentially arrested, because then the critical loads are no more closely spaced and there is well separated critical mode shapes, well separated mode of buckling, and there is no interaction. So, an interaction will not be significant. You see that? Good. So, the lesson from this is that whether it will be imperfection sensitive or there will be multiplicity mode also depends, not only depends on the geometry of the cell and its parameters, but also depends on the mode of loading. Okay, what kind of loading it is subjected to. one more solution I am going to present based on Donald's equation, and then we will move to the next. So, here the same cylindrical cell subjected to torsion. We are considering this, and here it is. So, this will be all, this is all twisted, right? You see, so there will be all this helical, this structure is a helical structure, helix or helical structure, right? So, you see that the wave will assume W is equal to W0 sine beta y minus alpha x, this, because this helix can be represented using this instead of multiplication of the two cosine or sine functions satisfying the boundary. Here we do not care about the boundary condition, please note that no inclusion of boundary conditions. Okay, it will be extremely difficult if you want to satisfy the boundary, it is not possible. Okay. So, W is equal to W0 sine, this basically mimics the helix, and then you substitute in the substituting in Donald's equation, right, in Donald's equation. And if you do substitute, and then of course here as you see where you will get nxy. Now, only the critical load you will get, the here there is no nx, there is no ny, there is only nxy. So, shear stresses, right, it will be expression n square by 2 r square k 1 plus yes. Where n is beta is alpha by beta. Circumferential wave numbers, okay, beta, and k is kappa is slope of helix. Slope means this one, okay. So, this one. So, when you take ratio m beta by alpha, then this slope will be there, right, with the longitudinal axis, this is the slope, okay, slope of helix or relative to the generating circle, the surface. Okay. Now, boundary conditions we are not considering because so it is somehow it is valid for a long cylinder in which I mean we are assuming that this solution is away from the boundary. So, whatever for far field solutions does not really influence by what happened here. See here in torsional buckling there will be much less number of wave number here, but here if you go there will be very small number of wave number here. So, okay, many wave will be there, but here relatively less, 1 or 2. So, from here if you do minimization, okay. So, by minimization, that is what we want to minimization, we will see that there is a condition to be satisfied, this slope of the helix 1 k square is equal to 1, and then you write nxy critical is equal to d n square by r square k plus e h k cube by n square half, okay, by if you do minimization. Okay. Now, that can further be simplified. See, k is very small, 1 plus k square can be taken as 1, okay, because in this expression 1 plus k square was 1, na? So, that is what we have substituted. So, ultimately, this expression we get. Now, this can further be simplified to be is equal to 0.1366 n e h by r to the power 3 by 2 1 minus nu square to the power minus 3 by 4. Here clearly you can see there is n here. So, minimum load will occur when n is 1. N is 1 means what? There is only one wave number here. But one wave number it cannot, it is not a physical thing, right? N is equal to 1 means what? A single buckle along the circumference, right? So, let me write it down, I will just write n k is basically slope of the helix and which is a very small actually. So, that is what this simplification can be made and then ultimately. So, what we see that nx critically is 0.136 n e h by r to the power 3 by 2 1 minus nu square to the power minus 3 by 4. So, here you see that n is equal to 1, then only nxy critical attains minimum. But n is equal to 1, the problem is that then there will be only single wave number here, and if there is a single wave number, it will not be able to satisfy the in-plane equilibrium equations. Okay. In-plane equation, see, Donald's equation is basically out of plane, right? For the in-plane one is automatically satisfied because we have introduced the stress function and the stress function is substituted. But if you see the in-plane equation, if you want to, if you substitute the strain displacement relationship, okay, and then if you derive, then there will be u and v, of course, in-plane displacement will be there. The problem is that in-plane equations I am not writing here, but it is not very complicated, okay. It is in fact much lower in order comparing W. So, in-plane equation, in-plane expressions I am writing, okay. In-plane expression, if you want to satisfy u is equal to u0 cosine of beta y minus alpha x and v is equal to v0 cosine of beta y minus alpha x. So, if you substitute this, the in-plane equations, the governing equations that will satisfy. The thing is that here if you see these are antisymmetric, that means if you twist it here, then you see the, the deformation pattern must have antisymmetric, right. So, a single wave number will not be able to accommodate this thing. So, that is what n is equal to 1 is not a viable solution. Therefore, viable solution, so this must be antisymmetric, okay, antisymmetric, okay. Antisymmetric distribution of axial displacement, antisymmetric of, and u and v are basically axial displacement. Axial displacement means, that is x, y, z. So, these are all w, right, and x, y, right. So, that is what. So, all this cross section is permitted to rotate with respect to longitudinal axis, that is what you have. So, the feasible one is basically for n is equal to 2 and n is equal to 2 is a viable solution, n is equal to 2 is a viable, okay, viable. So, when n is equal to 2 and if you substitute, then you will see that this is a viable solution for this, okay. The only thing is that we never talk about the boundary condition. See, it is difficult to satisfy boundary condition. because that will violate whatever simplification is that. But what happened actually, n is equal to 2 means there is 2 2 wave number in terms of the helix whatever you have assumed, right, because that is also conducive to satisfying the axial axial the in plane forces, that means in terms of u and v axial displacement, and that is why we require anti-symmetric field, right. But what actually happened that at the end boundary, that 2 buckles assumption is not valid. There can be number of buckles over there and at the boundary. Okay, that is not basically captured by the solution, but that doesn't cause a lot of much problem. That can be accepted as an engineering solution. Okay. Another interesting fact here, when the cell is subjected to torsion loading, it is not also it will the critical load. You can clearly see from here the critical this one are for different n1, 2, 3, they are not closely spaced, they are well separated, right. So, once again there is neither there is any mode multiplicity nor there is closeness of mode. So, there is no modal interaction and subsequent degradation of the critical load. So, as far as torsional loading is concerned, the cylindrical cell is not imperfection sensitive. Okay. So, just like lateral pressure, torsional load is also not imperfection sensitive. A cell, cylindrical cell under torsional load, torsional buckling, this buckling is not imperfection sensitive. So, with this thing I will stop here for the. So, you see that we have used Donel equation to solve the critical load for different cases. Please note that none of these solutions. So, the cases in which it is not imperfection sensitive, that means there is no multiplicity or closeness or mode. The Donel's equation give quite accurate good result, because that matches with the experiment. But the case in which there is huge modal interactions and multiplicity or closeness mode, then whatever we have obtained is not valid, because experimental load are way lower than the theoretical load. So, for which we need to consider the additional formulation. So, that is what we are going to do now. Okay. So, we could have directly used this thing, but we will use a different formulation for that. So, now what we will use, we will till now we concentrated on the critical, finding out critical load, different kind of under different kind of loading. Now, we will see the post critical load, post critical analysis of cylindrical cell. Okay. Post critical analysis means beyond buckling, okay, of cylindrical cell. And when we are considering post critical analysis, because we know that what kind of loading under axial, of course, we will consider a axial compression. Why axial compression? Because we know that the buckling modes are closely spaced and they are liable to interact. Okay. So, here the governing equations are. So, all these things will be very similar, except that you have to incorporate the initial imperfection, Initial imperfection we have to incorporate. So, epsilon xs is equal to del u del x plus half See, I am not deriving how this is coming, but it is not very difficult, it is pretty simple. See, all this was the in-plane displacement, this is von Karman nonlinear term, these are the additional term from the W is the out of plane deflection, W0 is the imperfections, okay. This is the imperfection amplitude, okay, imperfection amplitude, imperfection. So, there are additional terms is coming in the strain expression. You please note that del W del 0, this is the imperfection thing, this is the imperfection, this is the imperfection, okay. It's not difficult, it can be, if you consider the initial deformed geometry and we just do the way we derive the strain displacement, you will get it. So, if you substitute that thing in the stress function expression and then the way you have derived the equilibrium equation, then I will write down only the final expressions, okay. So, please note that these are very similar to the Donnell's equation, but we are not going to convert it into Donnell's term, okay. We will have two separate equations for the one for the out of plane the equilibrium in the out of plane directions, that means in z direction, and then another one is the compatibility equation that is expressed in terms of the stress function. So, we are going to write that. So, the one we are going to write del 4 del x4 plus 2 W del x2 del y2 plus del 4 W del y4 minus h upon d del 2f del y2 del 2w del x2 This one is the out of plane equilibrium equation, out of plane. As you can clearly understand that in terms of W, okay, this is the equilibrium equation, and then we substitute the strain displacement equation because of imperfection. Please note the effect of imperfection. So, this is effect of imperfection, this is effect of imperfection, this is effect of imperfections, okay. So, this is nothing but the equilibrium equation. Of course, is expressed in terms of displacement, but this is essentially equilibrium, out of plane equilibrium, equilibrium equation, out of plane direction expressed in terms of displacement, okay, out along z, out of plane, along z out of plane direction, okay. Now, the other one is the compatibility, that is what I am also writing, okay. So, the compatibility equation when we are writing, I will write this one something like that, del 4f del y4 plus del 4f del x4 plus 2 del 4y del x2 del y2 is equal to E del 2w del x del y square plus 2 del 2w0 del 2w del x del y minus okay, this is the compatibility, okay. Now, you can clearly see that the nonlinearity, of course, other than von Karman nonlinearity, we are not considering all the terms in the large strain, but the von Karman nonlinear term, okay. But they are of course available. So, these two equations, the equations are little big and complicated and nonlinear equations, okay. and it allows the redistribution of the in-plane forces, and of course, nxx is nothing but that can be derived from the second derivative of the stress function, right. So, we have to solve it, right. So, in the next class we are going to solve it actually, and using, of course, we will use this Galerkin method, and that method is given by Volmir. So, Volmir solution around 1967, it is a very little ad hoc solution, but this is a solution that can be discussed in the classroom, because otherwise this is a complicated thing. These equations can be solved to capture to demonstrate the post critical load drop actually, which is otherwise, and this solution is nothing, uses the Bubnov-Galerkin technique, Galerkin. So, this is based on assumption, we assume some W and we have some F, and then based on that we do. So, we will consider a cylindrical panel, we cannot solve a whole cylinder, but we will consider the case of a cylindrical panel. And then for simplification, so only one curvature is, so something like this, cylindrical panel, something like this, and then this one is R, this one is Y, this one is X, and this one is Z, okay. And we are going to consider that this is length A and this side is also length A, okay, both side length A. So, for simplification, so this, and we will assume that of course it is subject to some axial forces in this, and axial force, compression force from there, and all other things, these are other two ends are simply, all the edges are simply supported, all edges are simply supported, all edges are simply supported, because that will simplify the assumption of some solution, right, simply supported, okay. And you will see that how we will be able to solve it. So, this solution using Galerkin, Bubnov-Galerkin, then we will do that in the next class. Thank you very much for today's class, okay.